Welcome back, gamers, to our channel. Today we're going to be talking about Parik's theorem. It is a theorem about context-free languages. So let's get started. Make sure to hit that like button, and don't forget to actually, please don't subscribe. I'm Aska, and you'll hear from Mary in a little bit. We both met each other at GHP, so yes, that is a picture of us when we were 15. We were able to reconnect again for Automata, and we really just want to graduate because this is our last semester. So here's our table of contents. We're going to go through the background, let you know what you need to know before we dive in. Then we're going to go through the proof. Then we're going to go through the implications. What does it all mean? What's related? And then we're going to go do some closing remarks, wrap everything up. So for our background, this is some stuff that you need to know before you start actually reading the proof. For some extra background, Parik's theorem was actually published first in 1961, and it was later republished in 1966. And our parents were born in 1967, 68, and 69. So this theorem is actually older than both of our parents. Here's an example of a Parikh vector. Take the context-free language L, where L is a to the n, b to the n, c to the n. A string W that belongs to L could be something like 3 A's, 3 B's, and 3 C's. It must follow the rule. The number of A's must equal the number of B's, must equal the number of C's. If we disregard order right now and write W in the form of a vector where each entry in the vector is the number of each element, you would get 333 for our example string. Even though just seeing a vector like 333 isn't quite enough to tell if the string that creates that vector retains the necessary order to be a member of L, we can definitely tell that a vector like 454 is not a member of L without having to run a whole machine that recognizes L. So hold on to that because we'll talk about it later. Here's the formal definition of a Parikh image. Let sigma be A1, A2 to AK. It's just an alphabet, and the Parikh vector of a word is defined as the function P that goes from sigma star to n to the k, and that's given by P of W equals the length or the number of occurrences of the letter AI in each word W. The original word from the source used was Parikh vector, but sometimes it's also called a Parikh image or Parikh mapping. For simplicity's sake and for consistency's sake, we're going to stick with Parikh vector as that word that we'll be using for this video. So cool, but what does that even mean? We felt the same way. So here are some quick definitions that we should go through before we actually get into it. Parikh vector is just mapping an element of an alphabet to the number of its occurrences. So like the string that we had before or the string that we have right now, triple A plus 2 B's plus 4 C's, the Parikh vector for that would be 3, 2, and 4 respectively. And the Parikh vector of a CFL L is just the Parikh vector of all of the words in L as a single thing. When we say linear, that just means a subset S fits the form that you see on the screen right now. And there's an example of that. But what you'll see more often is the word semilinear, and that just means a subset S is semilinear if it's a union of finitely many linear sets. We'll also see the word letter equivalent very frequently. That just indicates that two words are letter equivalent if they both have the same number of occurrences of each symbol. So, for example, the string AABBCC is letter equivalent to the string ACBCBA because they have the same number of each element. So now we're going to get into the proof, and we're going to meet our good friend the pumping lemma in a little bit. So the theorem itself just says that each context-free language is letter equivalent to a regular set and has a semilinear vector. The gist of it is that if you let go of the order and you just ignore it completely, and you ignore the order of the terminal symbols in a context-free language, and you only focus on the number of times it occurs, you can interpret the language as virtually regular. Here's some setup for the theorem, the proof itself. We have a CFG where it will be generating a language L. P is the pumping length. Set U is going to be the set of non-terminals containing S. L sub U is going to be the subset of L that contains every word in L having at least one derivation from S where the generated non-terminals are exactly the ones we defined in set U. And each L sub U is letter equivalent to a regular set because all L sub U union together would be L, and there can be only finitely many L sub U. This also means that L sub U has a semilinear Parikh image. So if k is the number of non-terminals in U, then we're going to have f equal to a word in L sub U, and as long as the word is less than the pumping length to k, and G is going to be xy, where xy, the length of xy is going to be greater than 1 but less than p to the k. And we're going to have to prove that P of L sub U is going to be equal to P of FG star because FG star is a regular set. So we're going to have to do that by proving both directions. We're going to have to prove that the Parikh vector of L sub U is a subset of the Parikh vector of FG star, and we're also going to have to prove the other direction, which is the Parikh vector of FG star is a subset of the Parikh vector of L sub U. So I'm going to hand it off to Mary.
Yeah, so let's go into the nitty-gritty of this proof. So first we're going to prove that PLU is a subset of PFG. So before I go into this, to save some time, I'm going to go into just a brief overview of what these slides are talking about. If you do want to learn a little bit more and read in detail, make sure to pause the video and do that if you want. So first, if you have a string W, which is a member of LU, and W's length is longer than the pumping length, then you can delete a step in a derivation to make W prime, where W prime is still in LU. So if you keep taking steps of the derivation, off the derivation, then eventually you get some W prime where its length is less than the pumping length. So we can inductively assume that W prime is shorter than W. Therefore, PW equals PW prime XY, where XY is a member of G and W prime is a member of F. So with this, we've proven that PLU is a subset of PFG star. So going forward, now we can prove that PFG star is a subset of PLU. So if we let W be in FG star, then W equals W0S, where W is in FG star and S is in G. Now, if S equals XY, then there exists some derivation from A to XAY. So this is very similar to the previous part of this proof. We can inductively assume that PW0 equals P prime, where P prime is in LU. And from that, we can define PW prime prime equals PW prime XY equals PW0S equals PW. So since W prime prime is in LU and PW equals PW prime prime, then we have proven that PFG star is a subset of PLU. So finally, to wrap this proof up, we've proved that PLU is a subset of PFG star and the other way around. So from that, we have also just proved that PLU equals PFG star. And additionally, to prove the second part of this proof, if you let G be the form S1, S2 all the way to Sm, then PFG star equals PF S1 star, F2 star all the way to Sm star, which is semilinear. Now, let's go into some of the implications and talk about what this theorem can be used for. So the first of which is you can use Parikh's theorem as a shortcut to determine if a string W is not a member of a CFLL. So, meme review. Now, you can run the entire machine to see if W isn't in L, but you can now also use Parikh's theorem to see if W isn't in L. And with this, we're going to go back to our example from the beginning. So if you take a context-free language L, where it's A, N, B, N, C, N, where N is greater than 0, you can easily see that this example here, A, B, 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 C, 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 is of vector 3, 3, 3. Now, if you have another string that is 4 A's, 5 B's, and 4 C's, then the vector of that would be 4, 5, 4, and you can see that that is not a member of L without having to run the whole machine that recognizes L. So another implication of Parikh's theorem is that it implies some context-free languages can only have ambiguous grammars. Now recall that a grammar is ambiguous if it generates the same string in several different ways. Also, a CFL is inherently ambiguous if they can only be generated by ambiguous grammars. Now, meme review. So this next meme, if you see language 1 is 1n, 0n, while language 2 is 0n, 1n, and both of these where n is greater than 0. Now, to Parikh's theorem, L1 and L2 are the same. While they aren't inherently ambiguous, Parikh's theorem sees them as equivalent because it disregards the sequence of the elements. So if Parikh's theorem thinks L1 and L2 are essentially equivalent, It also implies that some context-free languages can only have ambiguous grammars. Now, these are called inherently ambiguous languages. Another use for Parikh's theorem is you can use it to prove if a given language is context-free or not. Meme review. So from here you can see that we have options now to find out whether a language is context-free or not. Originally we used pumping lemma, but now you can also use Parikh's theorem to do the same thing. So now I'll give it back to Oscar to make some closing remarks.
Thanks, Mary. We made it. We're done. Well, not yet. Here's another meme. The paper for Parik's theorem actually included a lot of different theorems to the point where we almost couldn't tell which one was the actual theorem we were supposed to be talking about. So we did use a lot of resources to understand the paper itself, and we wanted to kind of say thank you to those resources, which we used an entirely different paper for as well. And we also wanted to say thank you to the TAs, to everybody who was in this class that kind of let us not have to take a final exam. And instead we were able to do this cool video project. So smash that subscribe button, leave a like, turn your notification bell on, because I don't know if we're going to be back at this again, but it was definitely fun. So thank you.